Hey, it's Dr. J. Getting through chapter 6 this week, 6.3 today, the logarithms. So I'm going to tell you a little story about logarithms before we actually do any problems. Logarithms are related to exponentials, okay? So we are doing lots of exponentials. In particular, we do lots of multiples of 2. And so let's just do a simple example, something like 2 to the 8th power, some kind of exponential that you might have seen in one of the previous sections. And suppose you don't already know the answer. All right? Suppose you don't know it. Maybe you do. Maybe you don't. How are you going to figure it out? Well, you're going to multiply, right? You're going to multiply 2 times 2 times 2 times 2 times 2 times 2. Make sure you do the right number of 2's. You want 8 2's. Yeah. 1, 2, 3, 4, 5, 6, 7, 8 2's. So we're going to multiply 2 times itself 8 times. All right. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. It's just going to keep doubling. Then 32, 64, 128, 256. Okay. So then you do that, right? 2 to the 8th is 256. Okay. And then you erase it. Now, if I ask you right now, 10 seconds later, or 2 seconds later, what's 2 to the 8th? Oh, yeah, I think it's 256, right? But over time, in 6 hours, or in 6 days, or in 6 weeks, or in 6 months, or in 6 years, or in 6 decades, are you going to remember that that was 256? Are you going to recall what that was? Can you recall what that was? Well, maybe you can. Nowadays, in the modern era, you have a calculator that can just always, reproduce the number for you, so you don't have much incentive to actually recall it. But, our ancestors, going back hundreds and thousands of years, didn't have that luxury of, having a memory card or a memory machine that will memorize things for you. Your memory machine was writing something down. That's how you remembered it. So you could just write this down and keep it somewhere. That's exactly what a logarithm is. A logarithm is a way of storing the information that we just had, which was 256, so that if we come back to it 6 hours later, or 6 weeks, or 6 months, or years later, we can recall what that number was. Yeah. This comes from the Greek logos, arithmos. Both of these words are Greek. Logos, arithmos. That's what a logarithm really means. That's what the word origin is. Logos means to recall or to reckon. We don't typically talk like this too much anymore, especially here in California, but my grandfather used to say, I reckon. Yeah, I reckon back in 1932, when we was in the Great Depression, I reckon, right? But now we just say things like recall, but it really means to reckon or to recognize. Yeah, did I spell that right? And then arithmos, I think the word origin of arithmos is pretty easy to remember. It's where we get the word arithmetic from. The Greek word arithmos means number or numbers. So literally, logarithm or logarithm, logos arithmos, means to recall the number. So a logarithm is a way of recalling what we just did by writing it in what's called log form. Or logarithmic form. This is the way you do it. Okay? 2 is the base. 8 is the exponent, which I will abbreviate EXP. 256 is called the argument, which I will abbreviate ARG. So I want you to remember the argument, recall the number. Yeah, recalling the argument. Do you remember? I reckon we was arguing about it. You said it was 282. I told you it was 256. I reckon. Yeah, that's the whole idea there. And you're going to write it in log form. Okay. You're going to say log of the base, parentheses, argument. Notice the base goes down below. That's why it's called the base. And you're going to say it equals the exponent. This is called the log form. So for this example here, you're going to say log base 2 argument. Make sure you use parentheses. 256 equals 8. And this would be the logos arithmos, or the logarithm, base 2 of 256. You can also use lowercase letters or capital letters. It really doesn't matter. Sometimes we do a combination. We'll do a capital L and then a lowercase o and g. Whatever, as long as it spells the word log. You know, L-O-G is any way you want to write it. Some people even use cursive, you know. Yeah. Whatever you like, okay? When you're typing it on the computer, it's pretty forgivable. As long as you use the right 3 letters, it doesn't really matter, okay? All right, well, that's the backstory of a logarithm. This is what we're going to be doing for probably the rest of this week. I can imagine probably into next week as well. So example 1, rewrite each exponential into logarithmic form. Five squared is 25. 81 to the 1/2 is 9. 2 to the -3 is 1/8. All right, so rewrite each one of these into logarithmic form. So remember, it's log, base, argument equals exponent. That's how you reckon the number. That's how you're going to remember it. Okay, so log. Base is 5, so we put a little 5 down here. When you type that, you're going to do an underscore like this. So use the underscore. Okay. Then you're going to use parentheses. Argument 25 equals the exponent, EXP. There's only one exponent, which is 2. So log base 5 of 25 is 2. On your computer, you would type it just like that. Log underscore and then 5. Make sure you put parentheses around the 25. Otherwise, the computer will think you're typing 525. I'm not going to do that for all of these. This is one example of how to type it. I'm just going to do all of these out, and you can figure out how to type it. So you have log, the base is 81, the argument is 9, and the exponent is 1/2. You can also use decimals. You could say 0.5. I'm not sure if you remember this from a previous section, but the square root of 81 is what 81 to the 1/2 means. Halves mean square roots. So that's how I got 9, square root of 81. Here, I'll put that in a reckoning bubble here so you can recognize that. All right, and then we've done a lot of these. Right, negative powers, we spent a couple days talking about these. Negative powers are reciprocals. So you're going to say log base 2 of the argument, 1/8, equals the exponent, -3. Okay, you can also use decimals for 1/8. The decimal will be, what's that, 0.125 or something? 0.125. One type of exponential that's very easy to remember is base 10. Hopefully, when you were little, you memorized all your multiples of 10. Yeah. 10 to the 6th power, that's 1,000,000. 10 to the 0 power is 1. 10 to the -3rd power is 1,000th. So all the multiples of 10 are all the powers of 10 are very simple. You just count the number of zeros. If it's a negative power, you count the number of zeros, including the 0 to the left of the decimal point. I remember when I was in 5th grade or something, my teacher said, it's okay to write your answer like this. Right? And I wish she never would have said that, because I would remember, oh, okay, if I don't have to put that extra 0, I'll write it this way. And then I would always get this one wrong. I would accidentally write that because my 5th grade teacher told me I didn't have to write that other 0. So I tell my students, I don't care what your 5th grade teacher told you, you need to write that extra 0. All right? Because now it matches. -3, there better be 3 zeros, including the 0 to the left of the decimal point. Anyway, that's my little speech for the day. Okay. So rewrite all of these. So this would be log base 10 of the argument of 1,000,000. Yeah, that's 1,000,000, 6 zeros, is equal to 6. So this is called a common log, because one thing most of us have in common, hold out your hands, I can tell you're a human if you've got 10 fingers. Although there might be some other creatures that have 10 fingers. One thing that most humans have in common is 10 fingers. And so we usually omit the base and just write log of 1,000,000 is 6. So if you do not see the base, you assume that it's 10. I'll tell you a really bad joke. How many fingers do I have behind my back? How many fingers do I have behind my back, class? Can anybody answer the question? How many fingers do I have behind my back? Well, I'm a human being, so you know the answer must be 10. I know, it's a terrible joke. You always have, if you put your hands behind your back, you always have 10 fingers behind your back, unless you're missing one of your fingers or something. Or if you're one of these real, picky people that say a thumb is not a finger, but I mean, technically a thumb is a digit, it's a finger. So, all right, 10 to the 0. Let's just use the common log notation so we don't have to write the 10. We say log of the argument 1 is equal to the exponent 0. So this is for B, this is for A. For C, we've got log. You don't have to write the base. I know it's 10. In all of these, it's 10. Make sure you put the argument inside the parentheses, and then that equals the exponent of -3. So these are all called common logs. Let's do another one. Rewrite each exponential into log form. I probably could have just kept that instruction up there. But practice some of our E's from yesterday. Let's just do 3. These are some values that you might recognize from yesterday or from the day before when we were doing the natural graphs, the natural E exponential graphs. So this time the base is E. So you would say log base E of the argument 7.3891 equals the exponent equals 2. Well, the common log is 10, base 10, because we all have that in common. This is called the natural log, because this is called the natural base. So this is called the natural log. Now, I've always wanted it to be NL for natural log, but nobody listens to poor old Dr. Jordan. I still haven't been elected supreme leader yet. So it's not NL, it's LN, the natural log. It's Logarithmos naturalis. Yeah, the natural log, LN. All right. So I don't want you actually typing log base E, right? Although you could, if you really want to be the one that's different. It's not wrong. It's just not traditional. And so what we do is we write LN. You can use capital or lowercase or a combination thereof. So that's the natural log. Let's go through all of these. So e to the 0. So we'd say ln. You're going to do lowercase. The only problem with lowercase is if you're sloppy, sometimes your L's will look like 1s. Yeah? You don't even have to be very sloppy for that to happen. But as long as it's clear that that's not a 1. Right? If you're not sure, then use a capital L, and then you'll know. All right? Then do the argument. The argument is 1. And then equal that to the exponent, which is 0. Same thing here. Natural log. Here you can do a hybrid, half uppercase, half lowercase, just kind of giving you all the different options. The most important thing is where the argument goes. 0.3679. Argument always goes inside the parentheses. exponent is what the final value is equal to. So ln of 0.3679 is equal to -1. Okay, that's how it's going to work. You got your 3 different forms. You've got your log, base, whatever the base is. We call those other bases. There is a recipe if you like. Some people like recipes. So if you have ax equals y, that's going to be log base A of y equals x. So this gives you a quick way to go back and forth between the different bases. If the base is 10, then you may omit the base and just write the word log. And if the base is e, you may write ln, natural log. Notice the y goes inside the parentheses. That's the argument. The x goes outside, goes equal to x. That's the exponent. Pretty easy to remember. X, exponent. Y, argument. Why are we arguing? Yeah, why? Why are we arguing? That's the argument. X, exponent. And then you have your 3 different types of logs. This is what we call other base. So anything other than 10 or other than e. And then this would be 10, and then this would be e. Okay. You could memorize all 3 of these if you like. Personally, I only memorized the first one. I consider this a buy 1, get 2 free. Okay, example 4. Write each log equation in exponential form. So I'll give you some logs, and I want you to rewrite them into exponential form, exp form. I don't see a base, so the base must be 10. I don't see your fingers, so you must have 10. Yeah. Exponent is 5. Argument is w. I don't care what order this final answer is in. So if you put the w on the left and the 10 on the right, it would still be correct. Obviously, it's a quality. It doesn't matter which way you write it. All right, base is 3. Exponent is x. Argument is 10. All right, I'm not asking you to solve any of these problems. I'm just asking you to rewrite them. Don't actually solve them. It's not worth it. It's not our goal today. We will get to solving in a couple days or maybe next week. All right, this one has variables on both sides, so make sure you put them in the right order. The base is e because it's natural log. The exponent is p, and the argument is t. And again, these are two-way streets. You should be able to go back and forth between these relatively quickly and easily. You're going to have a calculator to do many of the logarithms, but there are some problems where picking up your calculator and typing in the buttons is way more work than it should be. In fact, the other day I spent longer looking for my calculator than I would have just by solving the problem on my own. So by the time I'd spent 10 minutes, where's my calculator? Where's my calculator? I probably already could have solved the problem by then. So I'm going to show you some problems that we can do without a calculator. I don't want to write all the parts down right now. It's going to have multiple parts, but I just want to talk about each part independently. So when you are evaluating a logarithm, it's very important that you read it in the following way. The word log, you should read this as what power? Yeah, power is a slang term for exponent. We often call it a power. Yeah. So what power of 6 is equal to 1? I really wish I would have been told this when I was 20, So when I learned this, I sat in my desk and I took my notes and I watched the instructor. And the instructor just said, log base 6 of 1, and then boom, gives you the answer. And learn it. Like, learn it. If you're not learning it, there must be something wrong with you, right? But I thought about this a lot. I thought, well, why are we calling it a logarithm? You get the story about the Greeks and the logos, arithmos, and all that. But, that really is what this means, right? The logos, arithmos is trying to reckon. Do you recall what power of 6 would equal 1? In other words, 6 to what power would come out to be 1? And hopefully you remember what power of 6 comes out to be exactly 1. 0, right? Do you remember? 6 to the 0 power would come out to be 1. So that means the answer is 0. Log base 6 of 1 is 0. If I went digging around for my calculator and tried to type that into my calculator, I would get 0. Yeah, but it's much easier just to reckon what is the power of 6 that would equal 0. Let's try another one. Log base 2 of 8. Again, read it. What power of 2 is equal to 8? Do you reckon? So 2 times 2 times 2. So recall 2 to the 3rd power is 8. There goes my pen. So this must be 3. Yeah. So what you're doing is you're remembering or you're recognizing how many times you would have to multiply 2 to get 8. All right, common log, no base. So this is a common log. So what power of 10 would equal 1/10,000th? Yeah, remember, 1 over 10,000 is the same as the decimal 1/10,000th. Yeah, 0.0001. It would be negative because this is a decimal. If it's a decimal, So if the argument is less than 1, or a decimal or a fraction less than 1, could also be a fraction, less than 1, then you know it's going to be negative. Count the number of zeros, 4 zeros, so that's going to be -4. You can easily check your answer. 10 times 10 times 10 times 10, 4 times is 10,000. And the negative means reciprocal, so it's 1 over 10,000. Sorry, I forgot to put ln. ln of the square root of e. So again, this is the natural log. The natural log is base e. So what power of e is the square root of e? Do you reckon? Do you remember what power is equal to the square root? Square root of e is the same as e to the 1/2. So this would come out to be 1/2. Square root is the same as a 1/2 power. You might want to make a note. The cube root would be the 1/3 power. The fourth root would be the 1/4 power, etc., etc. So depending on what type of root, I'd say in this class it's usually either a square root or a cube root are the two most common roots that we learned about. There are other roots out there, but it turns out in Math 10 we focus mostly on square roots and cube roots. Mostly in the interest of time, we don't have, 18 weeks to cover 15 weeks worth of material or vice versa. Okay. Decide how much longer we should go. Let's do a few more. Does anybody remember where I am? Example 6? Example 5? I'm not sure if I'm on 5 or 6. More evaluating. So evaluate these guys without a calculator. Okay, so let's go ahead and evaluate these without a calculator. So we have log base 3 of 1 over 81. So what power of 3 would be 1 over 81? Again, if the argument is a fraction, you know it's going to be negative. It's a reciprocal. What power of 3 is 81? 3 times 3 times 3 times 3 is 81. There's your reckoning. Remembering that 4 3s make 81. Yeah. The negative doesn't mean that it's actually a negative number. The negative means it's a negative exponent, which creates the reciprocal 1 over 81. Right now, we're doing this as an introductory concept. I don't have a lot of tools and properties. At some point, we'll have some properties that'll make that a little bit easier, a little bit more mechanical if you just follow a set of steps. All right, so I got what power of 4 is the square root of 256? This one takes a couple steps. First thing I'm going to do is write this as 256 to the 1/2. Yeah, square root is 1/2. And then I'm going to see if I can recall up here in my mind here. I'll use this mind now. 4 times 4, that's 16, times 4 is 64, times another 4 is 256. Now, I did say try these without a calculator, but you still have your calculator. So you could do 4 times 4 times 4 times 4 just to make sure you're not wasting a lot of time. That is, in fact, 256. So this is 4 to the 4th, and then you still have a 1/2 outside here. That's the square root. So this is log base 4 of 4 to the 2nd power. Combining the powers 4 and 1/2, 4 times 1/2 is 2. And so now it's what power of 4 is 16? Yeah, 4 squared is 16, so you just get 2. In fact, you could have just stopped here. Yeah. And so we have a nice property that we'll make this official in a couple more lectures, but we might as well see a property preview. We'll see it a little bit early. If you have log base A and the argument is also A, then you just get whatever the exponent is. So in this case, the exponent is 2, and so your answer is just 2. If the exponent was x, well, then the answer would just be x. We sometimes refer to this as an inverse or a cancellation property. This is a preview of that property that we'll get to in the future. I've kind of tread on this problem here a little bit. So this time I've got 2 to a power is equal to something. I don't know what that is equal to. But notice that my power is a logarithm. Notice my power is a logarithm. So if I have 2 raised to the log 2 power, these already have the same base. 2 and log 2 already have the same base. So it's like saying, what power of 2 is 2 to the 7th? Well, that's just equal to 7. As long as these have the same base, we can cancel them out. Very similar property to this, and you can just say that it's equal to 7. So another property preview. We're going to have a whole lecture on properties, but I'm just giving you little previews. If you have the same base, same base. So these both have to be A. In this example, the A's are both 2. So these are both 2. In this property, the bases are both A. You can cancel out them, the log base and the exponential base, and just say it's equal to y. y is the argument inside of here. So you just get your y is 7. So we often just refer to this as simplifying when you're using a property. So suppose you have log of the cube root of 10. Assuming this is a common log because there's no base. So this is log of 10 to the 1/3 power. What power of 10 is 10 to the 1/3? It's just going to be 1/3. That's it, as long as you've got that property. Okay. E and ln, those are going to cancel each other out. You're just going to get 4. These already have the same base. They're both base E. So I can cancel those out. This one's a little tricky. This is probably the hardest one. I'll probably have to stop here and let you guys absorb this a little bit before I get too far into the graphing and such is going to come tomorrow. So let's go ahead and just let this one simmer for a while. These do not match. 4 and 8 don't match. And you're not allowed to go 4 times 2 and make that 8. Right? You have to use only a 4. I want to have something like this. I want to have where they both cancel out. Either in this case, they were both 10. In this case, they're both E. So in this case, I want these both to be 4. All right. Need the same base to use the property. Right now, I'm just calling it the property. Again, it's a preview. You haven't seen the whole movie yet. So we're just looking at the trailer right now. So what is 8? Well, 8 is 2 cubed. Yeah, that's another way of writing 8. Well, what is 2 then? 2 is the square root of 4. Ah, that's what we're looking for. We want the same base. We want to use 4. So I can write this as the square root of 4 cubed. I can go ahead and bring the exponent outside of the parentheses, kind of like I did up here. The exponent goes outside the parentheses. I'm a little bit out of room now, so I'm going to have to work up here. So now I have log base 4. What is the square root from all of our previous logarithms? It's 1/2 power. Yeah, so the square root becomes 4 to the 1/2. So I've got log base 4 of 4 to the 1/2 all cubed. Combine the powers. Bring the power outside. 3 times 1/2 is 1.5, but I actually prefer a fraction, 3/2. And now you got it. Same base, You can call that the same base property. We're going to cancel these out, and your answer is just going to be 3/2. I would also accept 1.5. I don't think there's any issues with that as long as it's exact. But if you want to just keep with the way that I'm traditionally doing it, I would write it as 3/2. Okay, that's the introduction to logarithms. Tomorrow we'll start drawing the graphs. Yeah, and they're going to look a lot like the graphs that we did yesterday. They're, close relatives to the exponential functions, so you're going to have curves that look very similar to the ones that we did yesterday. Okay. All right. Dr. Jordan signing out. See you next time. Bye.